Hello everyone. So my name's Howie. This talk is about Scala build tools. So about myself, for those of you who don't know me, I've been involved in a lot of open source Scala projects. So things like Ammonite, Mill, JSON library, file system library, all that. I worked on dev tools at Dropbox Databricks, currently on sabbatical, so not currently employed. And I wrote the book Hands-on Scala Programming. So if any of you want to learn Scala or have learned Scala, this is a great book to get. Yeah? Speak close to the microphone. Okay. So this talk has 4 sections. We'll talk about what are the problems with the Scala build kind of experience. Can it be easier or is this the best you're going to get? Then we'll talk about the mill build tool. Like what is it? Why is it interesting? And what are the key ideas behind it that allow it to do what maybe other build tools are not able to provide? So first, can Scala builds be easier? I think the biggest problem with SBT is it is not easy enough to use. So it can be fast if used correctly. It can have good ID support if used correctly. It can be extended to do everything you want if used correctly. But the if used correctly part is maybe the biggest question mark. It doesn't matter how fast SBT can be if you cannot make it fast. Or it doesn't matter how flexible SBT can be if you cannot make SBT do what you want it to do. I feel that's a common experience, like maintaining SBT builds. I've done it for open source projects or proprietary projects. And it's always surprisingly challenging to do very simple things using SBT. Scala CLI is great, but it only really works for smaller projects that don't need that much customizability, like single module, maybe a test suite, and that's the max you can get. You won't be able to have custom source generators, custom artifact deployments, and all that. So in any bigger project, people often end up with SBT, and I think most of the Scala community uses SBT, with small fraction using things like Bazel, Gradle, or other build tools, and Mill. So just to go through some examples. Just running SBT is surprisingly difficult. Most command line tools, you run foo bar at the command line, it does what you want. SBT, you need to make sure you go into the shell, make sure you run stuff in the shell, you need to make sure you reload the shell, you might exit the shell by Control-C to interrupt your test, and you go back in the shell. And there's this small dance you need to do with SBT to make it work, and it's not difficult, but it's something that takes away your attention from what you actually want to do, which is your actual code. And if you do it wrong, you don't get the error. You do it wrong, everything just gets slow, and you might not even notice until you spend the whole hour or whole afternoon waiting for SBT to run and compile your code. So that's not a great experience, even though SBT in theory could be fast. One thing I bumped into recently was parallelizing tests in SBT. So all these configuration keys on the right interact in quite subtle ways to control how you parallelize tests. For example, we turn on parallel execution to true, but you're using fork equals true, then your test will not get parallelized. You need to also set test fork parallel equals true, but you also might need to set concurrence restrictions equals true, not the normal test limit, but the fork test limit. And it's quite, I just want to parallelize my test, but it turns out to be very difficult. For me, I took 2 hours. I asked for help on Discord because I just couldn't figure out the damn thing how to parallelize my test in the SBT project. And the test grouping also works. It also can make your test run a lot slower if you use it wrongly. How you use it correctly or wrongly is not very well documented, so you better make sure you know what you're doing and no one's going to tell you. The IDE support SBT is also worth mentioning. So let me open up an example project. So not this one. So over here, I have the Gatling codebase. So who knows what Gatling is in Scala? Is this open source load testing framework? I think they started a company around it trying to commercialize. But it's like a medium-sized Scala project built using SBT, about 24 sub-projects in the build file. You can see on the right here, and maybe 100K lines of Scala code, so quite a meaty project. So in any Scala project, you expect to be able to open up any file and jump to definition to see what the things do. So for example, let's open up a random file like Reddit DSL. I have no idea what this is. I see this Redis feed builder thing. I don't know what it is. I can jump to it. I see this, for example, find bugs non-null. I can jump to it, see its documentation. And this is the experience you expect in any Scala project. You see something, not even Scala, but Java, Kotlin. You see something, you jump, learn more. There's no documentation, no problem. Your IDE can help you explore and tell you what you need to know. But if you open up your SBT build, like here, some things you can jump to. For example, Gatling module, you can jump, see it's a helper around this project, enable plugins, disable plugins, logic. Gatling module settings, you can see it is a helper. It does tell you some information. But some things like, for example, library dependencies, You jump to this, you get nothing. You can't get stubs, which give you a type signature. If you set up the sources correctly, you can also get the source code. But I'm not sure this will work now, but we'll see. Let's say I get the source code, right? I know where the source code is. It's on GitHub. So let's go to keys. There's this file called keys.scala on the SBT repository. And let's say go to library dependencies here. So you can see that, okay, I have the signature, I have the documentation, but I can't really see where this guy is being used. Like, if I want to search library dependencies and see where it's being used, I basically have to search entire SBT code base and try and figure out which of these use sites is setting the value that I care about. Like, let's say, you all know what library dependencies does from muscle memory, but let's say it's a new plugin you are using, or let's say you're a new Scala user, you don't know what's doing, or let's say something's misbehaving, you're trying to figure out why, and you need to dig a bit deeper. All of these are cases where you need to kind of dig in, and you'd expect ID to help you. But with SBT, ID kind of helps you only superficially. You jump to definition, but definition doesn't tell you what the actual logic is here. Definition just gives you a stub that says, here's a signature, here's a name, that's it, and you're on your own after that trying to figure out where the values are coming from or where they're going. So that's ID support problem in SBT. The last thing is extensibility. So the first thing about SBT is that, in terms of extensibility, is that it has a lot of plugins. That is good. The bad thing about SBT is that it needs a lot of plugins to do anything, and that is not good. So, for example, Gatling has this big bunch of plugins by a whole bunch of different people. Some are half-maintained, some are unmaintained, some the guy got a new job, stopped using Scala, and you don't know which is which. And either you end up copy-pasting things and hoping it works, like what many people do, or when you start a new project, you do this like grand tour of the Scala open source ecosystem to assemble your Avengers team of all the different plugins you need to get your assembly jars working, or to get your like linting working, and all those basic things that everyone wants to do is a lot more difficult, even though it is doable. And when the time comes that you need to do something custom, which is often is the case, like often you can't get by with plugins and you need to do something special. So in this case, I'm using a small kind of straw man example. Let's say I want to count the number of lines of code in a project and save it as a resource file to use at runtime. So this is contrived, this is arbitrary, but this is no less arbitrary than the other arbitrary things you have to do in real projects, right? Maybe you have a custom bill of materials format you need to deploy in production for security scanning. Maybe you have a custom deployment artifact format you need to build. Maybe one team wants a linter, but the other team doesn't want to use a linter yet. You need to make that all work together. So all of these are real requirements that people need to do. And SBT, even a simple thing like counting lines of code can be surprisingly tricky. I showed you the code on the right. It's not rocket science, and many of you probably have done it before. I have done it before. But if you look at the actual build logic here, the build logic is totally trivial. You have the documentation string, I map, read lines, sum them up, I write it to a file. That's easy, and any of you should be able to write this in about 30 seconds without any mistakes. But it's the rest of the SBT config that is the part that you'll probably be fumbling around with, or copy-pasting stuff from Stack Overflow, or asking ChatGPT and getting it wrong. Things like, do you use task value, or do you use do you not use task value, or do you use dynamic task? Do you use compile and unmanaged sources, or do you just use unmanaged sources without the compile prefix? And all these things are solvable, but they are a lot trickier than you'd expect, given this requirement should be a 30-second implementation. And as the requirement grows, the overhead of trying to fit your logic into SBT grows correspondingly. So here is a bit tricky, can be done for a totally trivial customization. If you have a non-trivial customization that maybe takes a week to implement some custom pipeline, integrating SBT actually can be quite a big lift. It actually needs to go onto your weekly roadmap and so on. So I guess the common themes of this is that SBT can always do what you want it to do, but you may not always be able to get SBT to do what you need it to do. So SBT can be fast, SBT can be configured, SBT can have all the plugins or custom logic necessary, and you can always eventually find out what you want by digging hard enough, but it's a lot more challenging than you'd expect for even just trivial customizations or even trivial project that needs a linter and an auto formatter and an assembly jar deployment. So that's the problem with SBT, the kind of ease of use, more so than any other problem in the project. So let's talk about the Mill build tool. So Mill is the open source JVM build tool. It's been around a while. 2017 is 8 years from that ago, so it's been around for quite a while. Maybe many of the older projects that you guys have at work now. originally targeted Scala, now also targets other languages. It supports Java, Kotlin as first-class languages. So everything from like error-prone Java lint, Palantir Java format, KT format, KT lint, all that is supported, in addition to what you'd expect from like Scala format, Scala fix, and all the Scala tooling integrations. It mostly does the same things as existing build tools, but aims to be better in the ways you mentioned earlier. In terms of usage, it's used quite widely, although it's not dominant. So all of you use Corsair transitively. It's a dependency resolver. Most of you have probably touched Scala CLI. It's built using Mill. Some of you may have worked on Chisel or other related hardware-related projects. For some reason, those all end up using Mill. And of course, all my projects, like the MNight REPL and OSLib, FastParse, are all built using Mill. So that's kind of a short summary of what Mill is. A Mill build looks something like this. So it's Scala code. You have a package, you have imports, you have an object extend Scala module, you define things like a version of Scala, dependencies, maybe you have a nested test suite object. And in Mill, these objects become your modules. So the foo object means that in your foo folder, there's your submodule. In your foo/test folder, there's your test module. And these methods are the way you configure your Mill build. So in this tiny example build, you have foo.compile, foo.run, foo.test, foo.assembly. You can run the assembly later. That's convenient. You don't need a plugin for that. But basically all the same things you'd expect in any build tool. So nothing here is particularly special. Over here is an example HTTP4S build. And I can show it to you live, this one. So this is a HTTP4S project using the Ember web server and routing DSL with all the IO monad stuff. This is the Mill build we saw earlier on the slide. And there's examples here. So if I go to, let me open this up in my terminal. If I do, for example, Mill test, you can see it'll compile. The first one will be a bit slow because it's a JVM program, but subsequent runs get a lot faster, as you can see. You can compile test. You can, let's say I want to --watch run in the background. I can go to localhost and see it run. Let me open this into a new browser here. So here's my HTTP4S app. There's a to-do example app, nothing special. If I go edit the code, in this case, it uses Scala tags as a templating library. I can make to-dos uppercase, save it. You can see it picks it up, runs, and then it just updates the page. So again, this is nothing special, just showing that you can go beyond Hello World. It supports like your web server, web clients, live reload, watch and reload, and so on. So the next question people often ask is, what does Mill support or not support? And the answer is it supports basically all the Scala tools that you would encounter day to day from the open source ecosystem. So all the different packaging formats have built-in support. Different test frameworks, there are quite a number of them, including Java test frameworks and Kotlin test frameworks I didn't list here, but they're there as well. All the different platforms, including things like Kotlin, Kotlin.js, Scala.js, Scala Native, Spark, all the linters and publishing formats and so on. So all of this generally works. The internal stuff, like your custom deployment artifact that your own infrastructure team demands you build for them, that stuff won't be supported because I don't know what your infrastructure team is asking you to do, but all the open source stuff at least is mostly there. So that's a Mill build tool. That's a quick lightning tour of what it is and what you can do with it. So why is Mill interesting, right? Like Mill just does all the things you can do with Maven, SBT, Gradle, Bazel. Why do you care about Mill? And I think it basically comes down to ease of use again. And Mill does all the things that SBT does, but easier. And we'll go through them in turn. So first, in terms of performance, you use a Gatling code base as a kind of a case study here. So Gatling, 80K lines of code, 800 files, meaty project. Just as a proof of concept, we ported the build from SBT, which is what they use in open source. We translated it to Mill in a few hours, just manually. We saw the code was quite similar to SBT build. And we got it complete enough that all the tests pass on both. So it's just a manual translation to Mill, and everything works. There's the first approximation. So the thing you realize when you do these benchmarks is, as mentioned earlier, SBT really has two performance profiles, the obvious and slow performance, and the less trivial but much faster performance if you open up the shell and kind of juggle the shell yourself. And again, juggling the shell with reload and Control-C and going back in is not rocket science, but it's not something that you don't want to be spending your time thinking about when you also have many other things to think about in the day-to-day work. Mill is not faster than SBT in its hot mode, but it just does all the juggling for you. So Mill will create the long-lived server in the background. Mill will reuse the server where possible. If you kill the server, Mill will start it up again. If you change this config file, Mill will reload the config for you. Like, none of this is special, right? This is what you're already doing manually with SBT sometimes. And Mill just automates it. So you just run Mill from the terminal as like any other binary, and Mill will try and give you as good performance possible without you needing to think about it too much. So compilation is not the only thing that is important in a development loop. So we already saw watch and rerun. SBT has that too. It's convenient. Test parallelism in Mill is pretty straightforward. You just turn on test parallelism equals true, and we made it self-tuning enough that it works quite well for a wide range of performance characteristics, whether it's many fast tests, a few slow tests, tests spread across different submodules in your project. We managed to make it more or less work without needing too much fiddling, which is quite nice. Just turn on the flag and it's done. Probably will be the default in the next major version. Selective test execution. This is something that comes from like the Bazel world, where you can say, hey, check out main, take a snapshot, check out your pull request branch, what changed or what's affected by the changed code. And not just directly affected, but transitively affected. So for example, I can ask Mill to give me the tree of affected tasks, and I can say that, hey, okay, because you touched this example Scala web, this to-do web HTTP4S source folder, that is this test repo source root, which therefore invalidates test repo root, which therefore invalidates resources, which therefore invalidates test. And so we need to run that test, and we don't need to run all the other tests because the other tests are not affected. And then when you run selective.run, it only runs those tests. So this is very handy in CI. If any of you are using Bazel monorepos, Bazel also has this. If you can set it up correctly, Mill provides it. Kind of built in, pretty easy to use with just a few commands. You can configure your GitHub actions. We do that on the Mill code base, and it's very handy. Another interesting thing that Mill does is incremental assembly jars. So building big assembly jars with like 200 megabytes for Spark Submit can be slow. It takes 20-something seconds, maybe. Updating a big assembly jar can be very fast because assembly jars are zips, and you can update zips very quickly. You just open up the zip without unpacking it, take out the files that you don't want anymore, put in the new files, and that's your new zip. So there's no reason why SBT or maybe even other tools don't do this, but they don't, and Mill does. So for example, adding a new source file and recompiling and reassembling this after you've done it the first time takes 1 second rather than 20 seconds, which can really speed up things like Spark Submit, where people are iterating over an assembly jar that you keep needing to upload. The Chrome profile is interesting. So every Mill command automatically generates a profile. And let me go back to the Gatling code base. So this is so in my terminal here is a Gatling code base that we saw in the IDE earlier. If I do Mill like underscore wildcard compile all, double underscore just means recursive wildcard. Okay, first time we need to compile the build itself. This might take a few seconds and be a bit slow the first time. Then if I do Mill clean, sorry, it's the wrong Gatling code base. I need to go, oh no, it's the right one. Mill clean and Mill wildcard.compile. So you can see the prompt tells you what it's doing. First it resolves dependencies, it compiles everything, following the kind of dependency graph order as you'd expect. So that's not special, SBT does that too. What's interesting is that Mill provides this file called mill chrome profile.json. So this is a standard format that's used in the Chrome profiler. All of you have this Chrome : tracing on your profile visualizer on your laptops. Most of you probably don't know, but it's there, and anyone who has Chrome, which is all of you, can just open it up. So I can just take this file, even if the build is not completed and I'm still waiting if I can drop it in, and you immediately get a nice profile of where the time is going. So earlier we saw it took 20-something seconds to compile the whole Gatling code base. Well, this is where my 20-something seconds is going. I can see where my CPU is being used effectively. I can see where I'm bottlenecked. I can see where all these tests are depending on the core Gatling core test compile. And do you really need to wait for the entire core test suite to compile before starting compile HTTP test suite? Or is it to refactor that a bit to move the HTTP test earlier so you can finish the whole compile faster? So even if you don't know anything about Mill and you don't know anything about the Gatling code base, already you have some ideas of what can be improved just by looking at this visualization. And again, every other build tool can do this. The question is, can you figure out how? For example, Gradle, the way you do this is you go sign up for Gradle Enterprise, you go pay your credit card to Gradle Inc., download the Gradle Inc. self-hosted Velocity server, run this on your own AWS, send your Gradle build data to your self-hosted server, and then you can get build scans that basically give you this visualization. And Maven and SBT all have their own plugins that do this for you, and it just makes it really easy. So anyone just runs a command, you get this for free, and you can see, hey, where's my time going? Here's where it's going. No need to mess around with like third-party like plugins or servers. So that's the performance angle, right? Like, why is it interesting for performance? It's easier to run. You don't need to juggle the server. Easier to do things like selective testing, or you do things like visualize your performance profiles. It's just easy to do and get what you want done. Next thing we're going to look at is ID support. So again, we are just using Gatling as the case study here. So I'm going to open up the Gatling Mill build next to the Gatling SBT build. So on the right is Gatling SBT. On the left is Gatling Mill. Now let's make this bigger so you guys can see it. So over here is, this is probably not related. Okay. So I highlighted the build configuration for the Gatling core module in both Mill and SBT. Mill on the left, SBT on the right. You'll see that both build tools have slightly different syntax, but they mostly correspond to the same information. So Gatling core depends on netty-util, depends on quick lens, depends on common and JSON path, and the tests also depend on common tests and JSON path tests. So all of this is the same on both, and Mill needs the same configure as SBT does, so it can't make this stuff out of thin air. You need to configure it. Library dependencies, Mill calls it IB dependencies, same list of core dependencies. So in fact, Mill is a bit more verbose here than SBT is, which is very concise. So we already saw that SBT, some things you can jump, some things you can't, and you hit the wall. Mill is different. So for example, let's say I look at these fork arguments, right? So let's say I didn't know what fork arguments does. You guys can probably guess, but imagine you didn't know. Mill, you can see fork arguments, IntelliJ knows is an override. So it's an override of either Java module, assembly module, or run module's implementation. Let's say I go to run module. I can see fork arguments is in run module as a default value of empty string. Okay. I can search for where it's used. Fork arguments is used in runner. Runner is used in run background task. Do run background, maybe deprecated, ignore that one. Run fork task. Run fork task is used in run. And so you can see, kind of trace the logic of your build. You're not just configuring keys and hoping it does the right thing, and see where I'm configuring this, where it's going, what are the computations that are happening along the way, where it ends up affecting the thing I care about. Like configure fork arguments, but I want it to affect my run command. And how do I know what it's doing? You can just explore this logic in your IDE, just like you can explore any Scala, Java, Kotlin code base. And it goes the other way as well. For example, final main class. What's that? I don't know. Jump to it. Final main class is final main class optional. I don't know what's that. Final main class optional, either the main class that you configure, default none, or the local main classes. What are the local main classes? Local main classes are using class graph to discover the local main classes, which class graph is a kind of bytecode class file scanner. So you can go up and down your build graph in a way that you really cannot do in any other build tool. So SBT, you can't do this. Maven, you can't do this. Gradle, you can't do this. Bazel, you can do this to some extent with a bit of an asterisk, because in macros and other things in Bazel, it gets a lot more difficult. In Mill, it becomes really easy to explore in the same way you explore any application code base, and you already know how it works. Like, you already know how jump definition, find usages work. You know what overrides are, and IntelliJ knows what overrides are. That's why IntelliJ is able to provide this support here. So that's really the difference between SBT's ID support and Mill's ID support. Even though they both nominally have ID support, the Mill ID support is a lot richer, and it really makes you feel at home as an application programmer, kind of exploring your build and trying to figure out why it's not doing what you want it to do. So that's a demo. The last thing we're going to look at is extensibility. So Mill has a lot more built in than many other build tools do, and I think that's important because it makes it much easier to get started. So Mill does have plugins, but you often need fewer of them. For example, the Gatling Mill build, which is kind of more or less equivalent to the SBT mill build as a case study. It only needed an external plugin for Scala Fix, which is maintained by Joan Goyer. And all the other stuff is built in. So we have JMH support built in. Of course, it's the most popular benchmarking framework on the JVM ecosystem. Why shouldn't it be built in? Jupyter support built in. It's the most popular testing library in the whole JVM ecosystem. Of course, it should be built in. And so we just build in all of this stuff so you don't need to go and mess around with too many third-party tools. Even though you may need to at some point, it's much smaller lift than trying to configure a SPT project correctly the first time without copy-pasting, or maintaining this list of plugins as versions update and things get modified and evolve over time. So at some point, you need to extend your code beyond plugins, as we saw earlier. And the difference in Mill here is that while most build tools require you to be a plugin author to extend your build, in Mill you can just write code and use libraries to do what you want. And I'll show you what that means in a moment. So going back to our code, let me open up the other project, custom Scala. So here on the right, we have the minimal mill build for a Scala module. Like all the defaults, default source folder, default output folder, no dependencies, just a Scala version and a source folder name. If I go to this in the terminal, I can do mill like foo.compile, and you can see it compile, and that's it. So that's all you can do here. So let's say I wanted to do something like Bob mentioned earlier, right? Let's say I wanted to gather the line, count the lines of code in this module and add it as a resource. Let's say this is my requirement now. How do you do this in Mill? So in Mill, you can say def line count is a task. I need to depend on other tasks. I can ask IntelliJ what other task is this. You can see there are a bunch of source tasks. You might not know which one you want. You can again ask IntelliJ what the different source tasks do. That's very convenient. Let's say I want all source files. And let's say I map it to the file. I want to read the lines on the file path dot size, and then sum it up. Let me just format this nicely. So that's all I need to do to declare a custom task in Mill. And now I run this, I can say mill show foo.line count from the terminal. You see it has 17 lines of code. That's how much it has in this source file. I can do mill inspect foo.line count from a terminal. You can see Mill automatically gathers everything. For example, it grabs your Scala doc, so you don't need to go and copy paste it into a string. It has all source files captured for you, so you don't need to go have a separate dependency on it. Line number, file name, all captured for you. That's quite convenient. So this is defining custom task account lines, but we haven't integrated it into resources yet. And the way you integrate things into resources in Mill is using overrides. So you say override def, like what? Let's say what do you want to override? Well, Mill has a bunch of tasks. Again, you can ask what the different tasks are, whether source jar, doc resources, compile resources. In this case, I just want the normal resources. And I can say, I'm going to write to this task.des folder, which I'll describe in a moment, the line count, call the method as a string. And then I'm going to append a reference to the task.des folder. So somebody may be asking, what's this task.des thing? Well, in Mill, every task gets its own folder on disk to write stuff to. So what's one of the big problems with reading and writing to disk? It's a global side effect. I may stomp over your files, you may delete my files, you may erase writing files to disk, all sorts of problems because of this global mutable file system. Well, in Mill, we say all of you, every task is a separate folder. So which means that this global mutable file system becomes a local mutable file system, effectively. And if you follow the convention, which is you only write stuff to your own folder and don't mutate other people's folders, this global mutable to local mutable will actually become the local immutable file system. Your files become like immutable values. You don't need to worry about race conditions, don't need to worry about collisions, don't need to worry about coming up with names of where to put them, because they'll always be put in the same place according to the name of the task. That's what this task.des folder is. So once I've done this, so I've overridden resources, I add super resources to the reference to the new destination folder. I can do mill show foo.resources. Over here, you'll see that I have my normal foo/resources folder. That is a super. All of you already know what super does, but you learned in Java 101 15 years ago. And you have this out/foo/resources.des folder. This is the task.des folder we mentioned earlier. So every task is a separate one. They will never collide. I can see what's in this out/foo/resources.des. There's my line count.txt. You can see contains 17. I can do mil foo.run, and the runtime code will then be able to read the line count at runtime as a resource. In this case, it's just a small example Java program that users get class over the resources tree, and is able to get my line count at runtime. So again, this is a kind of synthetic, contrived example, but it just shows how easy it is in Mil to just customize it what we want with full ID support, full type checking, normal Scala code, so no colon equals, no weird like dot task value. You're just writing methods, you wrap each method in the task, and you call other methods. And that's, you write Scala doc, and that's what becomes your Mil build graph. So let's take this one step further. Let's go into, let's say I want, instead of a line context file, I want a HTML file. Let's say I want to pre-render some HTML to improve performance at runtime for like, some static web server. Not unreasonable. How do I do that? Well, Mil doesn't come bundled with any HTML templating engine. You try and do this, it'll yell at you and say that doesn't exist. What Mil does let you do is it lets you import these libraries kind of on the fly in your build file. So I can start to import my commonly how we Scala tags 0.12.0 in my IDE. I can reload it in IntelliJ, or equivalently, I can run it here. The console's waiting for IntelliJ. Okay, so now IntelliJ is reloaded. You can see it's now recognized. I can jump to it. I can show it in my IntelliJ external libraries, and I can start using it. For example, def HTML snippet equals a task. Let's say a div h1 like line count, and a paragraph line count as a string. And if I put my HTML snippet here instead of the raw line count, and I do foo.run, oops, I need to call render because I need to make a serializable, JSON serializable value. I can now, you see that I'm now pre-rendering HTML at build time to make available at runtime using third-party libraries like Scala tags, as well as custom logic like this, source files, .map, readline, size, sum. You can see the file on disk. The file on disk, if I do mil inspect or mil show foo.html snippet, you can see if I go to like out foo html snippet.json, you can see my HTML being pre-rendered and cached in this JSON file. All that's done automatically for you. So you just write your build logic in your code, and you get a build pipeline just like that. So I think what's most interesting here is that there is no Mil HTML rendering plugin. There is no Mil line counting plugin. And in other build tools, you may have to go find one, or you may have to go become plugin author yourself and say, hey, how do I integrate with this plugin API? In Mil, you just write methods. You write other methods. You can use any libraries you want, including the same libraries used in production, if you so desire for consistency. You can override things, like you learn in Java 101. You can call super. You all know what super does. And that's how you configure your build. You already know how to do this. And you already know how to write Scala. So that's how you do it in Mil. So this is a demo we saw live. No need to go through the slides. So that's extensibility angle. The built-ins are much richer, and just programming Mil to do what you want is also much easier. So what are the ideas behind Mil? Like, why can't everyone else do this? Like, surely everyone else also wants easy performance. Everyone else also wants good ID support, right? Like, why does SBT or Maven or Grail just go fix ID support? And I think the reason is that Mil has some really interesting ideas, foundation of its architecture that are different from all the other build tools, and that's what lets Mil give you these concrete benefits I've shown earlier. So the first one we're going to look at is the idea that build graphs are pure functional programs. So this is not obvious, right? Like, you look at many build tools, you define a task, you read stuff off disk at some arbitrary string path, you write stuff from arbitrary point on disk. All your tasks are just like side effecting methods. That's very common in like Rake, in Make, in CMake. All of these build tools, you're just writing tasks that just do stuff to disk, and who knows what they do. And you have to make sure you keep them straight in your head. Mil has a different idea. Mil says that, well, most of your build tasks are do thing to input to make output. In Mil, it's spelled like def output equals task, do thing, input, but it's the same meaning. It's just a different spelling using Scala syntax. And you look at the things that build tools do. Almost everything a build tool does is in this format. Whether you're resolving dependencies to make jars, and I don't know if you all know, but Maven Central dependencies are immutable. So you can even treat them as, even though it's a network call, you can kind of treat the Maven Central as an immutable data store with read-only values that can never change. Codegen, IDLs, you make source files, compiling the source files to dependencies, make class files, and all of the things you do in build tool with a star, not quite all, but almost all, 99%, are pure functions with some asterisks. For example, you must write to this, you must go to the network, but practically they're pure functions. And if you look at, for example, the pure functional way of writing line count on the left and the imperative way of writing line count on the right, what's the difference, right? They both have the same logic. They both do they'll both like loop over all the source files, read things, count the number of lines, write it out to disk somewhere. But the difference is that for the functional ID on the left, for functional implementation on the left, Mill knows where the data is going to be written to, because you're not writing it, Mill's writing it. Mill knows what the inputs are because you're not reading from some random string off disk. You are just depending on upstream task, and task gives you the values. So that means that the thing on the left here is side effect free pure function. And what do you know of pure functions? They're easy to parallelize, they're easy to cache, they're easy to rerun because they won't have weird side effects messing things up, they won't collide, they won't have race conditions. And on the thing on the right is global side effecting. You get the complete opposite. You can't really cache it safely. You can cache it sometimes, but sometimes it'll screw up. You can't parallelize it safely because sometimes it'll collide. All the bad things you know about global mutable state. But even though it's the same logic, it can be run in both. And so Mill chooses a pure functional approach. And that's what lets Mill do all this interesting parallelization, caching, and scheduling without you needing to think about it at all. So you just write business logic, which is in this case, map, read line, size, sum, done. That's my task. And pure functional programming is what makes things like jump to definition useful. So for example, on the left is SBT, right? You look at unmanaged source directories, you jump to it, you get a stub. What's this? It is a global mutable variable. Someone else is going to assign the value to the stub later. Someone else is going to read the value from the stub later. But when you jump to it, you just get the stub. You don't know who's assigning, who's reading. It's just, there's nothing there. It's just a global mutable variable. On the right, from Mill foo to all source files, the syntax is a bit different, but that's not the interesting part. The interesting part is when you jump to all source files, you get the implementation because it's not a global mutable variable, it's a pure function. You jump to it, here's implementation. You see all sources, you can jump to it. You can see sources, jump to it. You do not find source files, you can jump to it. And the fact that Mill works with pure functions is what makes ID support really useful. Whereas, for example, in big Java projects, you jump to global variables, it tells you nothing. In Scala pure functional projects, you jump to definitions, it always tells you what the value is being computed from, and that's what makes it very valuable. So that's the first idea, build graphs are pure functions. The second thing is object-oriented build definitions. Who here loves OOP, object-oriented programming, Java 101? Not many people love it. Well, here's some reason to love it. So when I say object foo extends Java module, this is really a Scala object. It's not some special pseudocode syntax. Like, it's really a Scala object. This is really a Scala abstract class or trait or whatever you call it. These are normal Scala imports. And so this is really just Scala object-oriented code. And when you inherit a class in an object, you inherit its methods. You learned that 15 years ago in Java 101. These methods call each other. And in Mill, the method calls become the task dependencies. The method call graph becomes the task build graph. So when you add, for example, a new task or new method that calls another task upstream, when you override the task and call super and also call your new task you added 5 minutes ago, you already know how all this affects your build graph because these are just method calls and you know what override, super, and method calls look like. And once we have this build graph, Mill can then do interesting things. For example, Mill can parallelize, compile, and line count automatically because Mill knows that they don't depend on each other. You don't need to tell Mill, Mill can do that for you. Mill knows that assembly needs both of them to finish first, so Mill can schedule that appropriately later. Mill can assign every task place on disk. This is what I mentioned earlier with the .destination folder. So foo.line count doesn't write any files itself, it gets a line count.json file. Foo.compile gets a foo compile.json file for its metadata and compile.des, which is a destination folder. And these will never collide. So foo assembly is its own assembly.json, own foo assembly.des, and they'll never kind of muck over each other on the file system. Lastly, when you do validation, for example, let's say you touch the resource folder. Well, the resource folder, original resource folder, is now super resources because we overrode it. And Mill can just do a breadth first search and say, okay, resources change, foo assembly change, I need to regenerate the assembly. Mill knows where the assembly files are because Mill controls that path, so Mill knows what to delete and where to put the new files it recreated. And mill also knows that compiler and line count do not need to be recreated because they are not downstream of full super resources. And mill also knows where to get the data off disk because it's cached by mill at the standard path, full line count.json, full compile.json, and compile.dest. So what's most interesting about this part is there's no code here related to parallelism or caching at all, or dependency tracking, or graph building, or other things like that. You just write your build logic, which is counting the lines of code in the source files, writing a file and adding it to your resource path via ++, and mill handles everything else. You don't need to write threads, you don't need to write executors, semaphores, locks, async. You don't need to write cache and validation algorithms, write your own cache on disk, put stuff on Redis or in your own database, calculate cache keys. You don't need to go register your depend zones or your file inputs, file outputs for each task. Mill does all of that for you, and you just write your build logic, more or less pure build logic, and mill handles all the build tool stuff. So that's the old build definitions. The last thing we're going to talk about is the idea of a direct style DSL. So both mill and SBT are Scala, but the mill Scala on the left looks a lot more like the Scala you write every day than SBT Scala on the right. You don't normally use lazy val, task key, colon equals in your day-to-day code. You write objects, class, superclasses, and defs, and method calls. So that's what mill does. And one way I look at this is that SBT is really a two-stage program. You have your stage one where you're evaluating Scala, where you have things like Scala doc, super, objects, lexical scope, methods, defs, all that nice stuff. You know all the stuff on the bottom right. IntelliJ knows stuff all on the bottom right, so that's great. But the problem with SBT is that the interesting stuff is the stuff on the top right. Things like the four-dimensional scoping hypermatrix. Like who here thinks about tesseract scoping every day? Like, I don't use tesseract scoping regularly. I use lexical scoping. So when I look at SBT's four-dimensional scopes, it's really difficult to kind of understand. And things like, for example, the SBT doc strings are different from Scala doc. So IntelliJ doesn't know that they are doc strings. IntelliJ can't show it to you in the help. So all of these things, although they are not super complicated, they are sufficiently different from Scala to confuse users and also confuse IDEs who can help you with this stuff on the bottom right, but cannot help you with the stuff on the top right, which actually proves to be very important. Mill does a different approach where it kind of works heaven and earth to squeeze everything into the bottom right corner of this diagram. So mill Scala doc are your doc strings. You can't access doc strings at runtime normally, right? So that's very hard to get. So mill has a compiler plugin that will parse the Scala source file, grab the doc string, and put it in a Java annotation, and for you to use at runtime. And sure, it's kind of annoying to implement that. Once it's implemented, it's really nice to use because you just write normal Scala doc, and it gets picked up for you at runtime. You don't have a separate string that gets used at runtime. Similarly, like the mill methods are just tasks. The mill call graph is a build graph. There is some magic to capture the build graph and turn it into a data structure. You can't normally capture method call graphs, right? But mill does magically capture these. But as a result of this magic, it all fits into stage one, which is the things that the tools like IntelliJ and developers like all of you and your junior folks you hired out of school understand. Everyone understands inheritance, everyone understands loop and overrides, everyone understands lexical scope, and that's what mill needs from you. So you don't need to really learn much to use mill. And maybe one interesting thing I want to mention is mill is actually a kind of applicative effect system. So who here uses effect systems like CATS or Zio or whatnot? So most effect systems are full of flat maps. You have these monad M things everywhere. And if you look at this mill example that we wrote earlier, you'll see that there is this strange T wrapper here. So there is like a task effect system wrapping all these values in mill. Like we do, it's not monadic, it's applicative, so that allows us to parallelize things a bit more easily. But the mill makes it so seamless that most of you probably didn't even notice. You thought you were just calling methods and defining methods that call other methods. And we, on the back end, lift it into this effect graph thing. So we get all the benefits of the effect system, but without all the user-facing confusion that happens when you take like a new grad and try and throw them into a CATS effect Zio code base. Because like from this example, the new grad can just think it's Scala or even just think it's Java, and they'll be 99% correct, even though 1% is a bit special. So those are key ideas behind mill, and this is the last slide. So I think the long and short of it is, if you are not happy with SBT or your other build tools for whatever reason, you should definitely try out mill. There's a lot of interesting There's a lot of interesting ideas, things like the pure functional builds, object-oriented builds, a direct style, DSL. And these interesting ideas aren't just academic. These interesting ideas give you things like ID support, you all like ID support, performance, extensibility. So the documentation's on the bottom, the GitHub page, my email, if anyone wants to contact us later or try it out. All the examples on documentation are integration tested and downloadable, so you can download the zip file and just run it without any install. And that's the end of the presentation. Thank you.